Hello again. We're going to begin a new discussion, kind of building on what we talked about when we first started talking about calculus, and that's going to be limits of sequences and functions. So let's get started. We kind of talked about this before. We were talking about limits as they pertain to asymptotes of rational expressions. So as you recall, if we saw a rational expression that was top-heavy, meaning that the degree on top was bigger than the degree on the bottom, then what we noticed was that as x approached infinity, then that expression would also approach infinity. All right, and then if we look at an expression that is bottom heavy, meaning that the degree on the bottom is bigger than the degree on the top, then as x approaches infinity, that expression will approach 0. And then the last case, what if the degrees are equal? If the degree on top is equal to the degree on the bottom, we call that middle heavy. And the way to figure out the limit as x approaches infinity is just to find the ratio of the lead coefficients. So that's going to be an actual number like 6/5. All right, so how does this apply to sequences? Now that we're talking about sequences instead of functions that are expressions. Okay, well, a sequence kind of behaves the same way, but the sequence uses integers that are greater than or equal to 1 for values of n. So n equals 1 would be the first term in the sequence, n equals 2 would be the second term in the sequence, and so on. But the rules are still the same. So we're using n instead of x, and we're thinking of n as being all positive integers. So as n gets bigger and bigger and bigger, more positive and more positive, a top-heavy expression as a term would also approach infinity. A bottom-heavy term would approach 0, and a middle-heavy term would approach some constant. So the rules are still the same as they were for functions. Let's talk about why this happens. What we can do whenever we have an expression like this is we can divide the top and the bottom, every term in the top and the bottom, by the highest exponent of n. So in this case, we can divide everything by n to the third, since that's the largest exponent of n that I see. Well, what's going to happen is 3n to the third will become just 3, 4n will become 4 over n squared, 1 will become 1 over n cubed, 4n squared will become 4 over n, and that minus 5 will become minus 5 over n to the third. And as you know, when n approaches infinity, if I have a fraction that has a constant on the top and n to any exponent on the bottom, that fraction is going to approach 0 as n approaches infinity, because basically I've got a constant on the top and a number that's getting bigger and bigger and bigger on the bottom of that fraction. So of course that fraction is going to approach 0. So that's why I crossed all those fractions out and replaced them with zeros as n approaches infinity. So what I end up with is 3 over 0, which I can think of as a limit not existing or being infinite in one way or another. Okay, let's look at another example. This time it's going to be bottom heavy, where the highest degree of n is on the bottom of the fraction. I'll still follow the same steps. I'm going to divide everything by n to the fifth. That's going to make 5n to the fourth into just 5 over n. 7n will become 7 over n to the fourth, and 12 will become 12 over n to the fifth. And then on the bottom, 9n to the fifth will become just 9, and 8 will become 8 over n to the fifth. And again, I will cross out any fractions that have a constant on the top and then some exponent of n on the bottom. And as n approaches infinity, those fractions will approach 0, leaving me with all zeros on the top and a 9 on the bottom. So as n approaches infinity, this term will approach 0. And then the last example, again, I've got n approaching infinity, but now I've got n to the same exponent on top and on the bottom. N to the 7 is my highest exponent of n. Okay, so I will divide everything by n to the 7, and the same thing happens. 6n to the 7 becomes just 6. 8n to the fourth becomes 8n to the third. Negative 1 becomes negative 1 over n to the 7, and then on the bottom, 5n to the 7 becomes just 5, and the negative 3 becomes negative 3 over n to the 7. And again, any term that is a fraction with a constant on the top and n to some exponent on the bottom will approach 0 as n approaches infinity. So I've got 6 and a couple of zeros on the top, and then I've got 5 minus 0 on the bottom, and that means I've got 6 over 5. All right, so that's why those rules of top heavy, bottom heavy, and middle heavy exist. So now there's another case that we need to talk about in this chapter, in this lesson. If an expression has radicals, instead of being just an expression that has a polynomial on top and a polynomial on the bottom, what if it has radicals instead? Well, one thing I can do is I can multiply top and bottom by the conjugate of this expression. So in this case, instead of that root minus n, I'm going to multiply top and bottom by that root plus n on top and bottom. And that's like multiplying by 1, so it's okay. So if I multiply the numerators together and I do a little bit of distributive property, then I end up with n squared plus 3n minus n squared on the top, and then I've got the same thing on the bottom that I had in the previous step. Well, what happens is if I simplify the numerator, those n squareds will subtract out, leaving me with just 3n on the top, and the denominator the same as it was before. So now what I can do is I can divide top and bottom by the highest exponent of n, just like I did in the previous examples. But just remember that when you're inside of a square root, dividing by n is the same thing as dividing by the square root of n squared, okay? Because that's the same thing as n. So that 3n is going to become just 3. The root n squared divided by root n squared will just become root 1. And the root 3n divided by root n squared will be root 3 over n. And then on the outside of that radical on the bottom, I've got n divided by n, which is just 1. Okay, so you really have to be careful when you're dividing by n inside of a radical. Make sure you adjust your exponent. So really the only thing that crosses out is that 3 over n inside the radical, and once I simplify, I end up with 3 over 2. So as n approaches infinity, the nth term will approach 3 over 2. So that is this lesson. If you have any questions, please let me know, and I will see you tomorrow.